In the last lecture, we started talking about the strengths and limitations of climate models. This is necessary because there are two groups of people. There are those who think that climate models are not very good, you cannot trust them. And many climate change deniers belong to this group. So when IPCC made a prediction about warming of the earth over the next 20 years, they said we cannot trust it because the models are not good enough. There are others who are impressed by the complexity of climate models and the kind of techniques used as well as supercomputers used to make predictions, and they think models are great. Okay? The reality is somewhere in between. Models are quite good for certain purposes, like the global mean temperature, but they are not so good if you want to know whether the rainfall will increase in your city, for example. That's a tough prediction to make as to how rainfall will change in a small area. Okay? So this is important to understand this difference. So I'm going to give various examples to show where the models are doing well and where they are not so good. Okay? And that's what Professor Michael Mann's statement here, which I quoted at the end of the last lectures here, that models are fuzzy, there are some problems, but for overall warming of the planet, they are quite good. Okay? And here is one example from IPCC which shows how useful a model is, not for future prediction, but to identify what causes the warming. For example, so here is two figures. On the top, black is the observation of the global mean temperature change from 1860 to 1900, and there are two simulations, the CMIP-3 and CMIP-5, the coupled model intercombustion project. In this project, if you don't allow carbon dioxide to increase, as we have observed in the last 150 years, the models show no warming. Okay? The same models with the same initial start, if you put the increase in carbon dioxide, immediately they agree with the observation. Okay? Not perfectly, there is a slight higher value here, our 0.1, 0.2 degree. That is not surprising because, as you saw in my last lecture, aerosols play an important role in cooling the earth, and we are not in a position to precisely define how much aerosol is there of what kind. Okay? But if anybody doubts whether carbon dioxide really causes warming, that is resolved totally by these two simulations. They show beyond any reasonable doubt that it is carbon dioxide and carbon dioxide alone which can explain the rapid warming in the last 60 years. Okay? So that's one good use of climate model. But you must also realize that when you look at a climate model, you must also ask yourself what is the application you're looking for. See, climate model has to resolve various scales of phenomena occurring on Earth. One at the global scale, waves which travel along the planet, cyclones and so on. Their scales are 100 to 10,000 kilometers. Those are fairly well simulated by climate models because typical grid sizes 50 kilometer latitude longitude, so they do well. But if you are interested in local clouds which are of the scale of 10 kilometers, the models are not good. And if you are worried about turbulence and cloud microphysics, that is droplet size, ice particle size, models cannot do well because they don't resolve it. Okay? They are put in the model empirically. It's not from first principles. So you must remember that the models are good for large scale, not so good for small scale. Now this is a problem because whenever you talk to people about climate change, they are worried about the impact of climate change in their city or in their country. If the country is small, then these models may not make a good prediction for that country. Okay? The models are good for global scale, continental scale and so on, but not good on a smaller scale. So that must be kept in mind when you look at a model output. So model outputs are good for a certain purpose, not good for certain other purpose. So the other thing is that you cannot depend on one model and one simulation, because you know the Earth system is chaotic. There are lots of things going on there and many things are non-linear. So you shouldn't depend on one simulation. So you should make many simulations with slightly different initial condition, because the initial condition is not perfectly known. So there will be some errors in that. So that should be accounted by starting from slightly different condition and looking at the future. And secondly, you should look at more than one model. No model is perfect. There are some models good for certain purposes, other models are good for some other purpose. So it's better to look at average of many models and many simulations. This is what's called ensemble, average of many simulations of many models and many conditions. Now let's clearly understand for what purpose models do very well. But suppose you want to know how the extreme cold events and extreme heat events are going to change in the next 50 years, models are very good. Okay? And I will explain to you with the figure on this side why it is so. Because you have good data for the last 100 years and good understanding of how extreme events occur. Okay? So we understand the physics and the model can also simulate it well. Here is an example from Central England, which has the longest data of temperature in the world. They have shown here the temperature distribution in different years, okay, in summer in Central England, and in the period 1961 to 1990, it was 15.3 degrees centigrade average, but there was a variation from 12.6 to 17.3, year-to-year variation. Okay? And by the time we come to 2050, which is only 25 years from now, you see that temperature has gone to 16.9 and the distribution shifted by about 2 degrees. Okay? And because of that, you can clearly see that Central England is experiencing very hot climate in summer, which was never there in this period. Okay? These are extreme events because people live in England for the past 100 years hardly saw these temperatures. They mostly saw in this range. Okay? So this can be easily seen that a slight shift in the mean value immediately increases the extremes. And as shown by this shaded red, it has gone up from being about 1% of the area under the curve from 1960 to 90, it becomes 33%. So what used to occur 1% of the time now occurs 33%. So almost 30 times increase in the extreme events. So this is what everybody is already seeing, whether in India or in Europe or in Canada. There are heat waves which are killing people because extreme events are increasing, and this is well understood physically and the models are simulating it very nicely. Okay, no problem. Now the next important issue we are all worried about is droughts. Droughts is very important for all of humanity because droughts affect our food production. Okay, whether you are in United States or in Europe or in India, if there is a major drought, your food production goes down, so the cost of food goes up and has a huge impact on economy and the people. Okay? Unfortunately, our capability of predicting droughts is not very good because we don't have good enough data to accurately monitor droughts, and the models are also not very good at predicting droughts. Okay? Same thing for extreme rainfall, which cause floods. Rainfall above 50, 100 millimeter per day is occurring more often now than 50 years ago. And although that can also be explained by the same kind of curve, you draw the distribution of rainfall 50 years ago and 25 years later, you see a similar distribution. We know the extreme rainfall will increase, but the mechanism which causes the increase in extreme rainfall is not that well understood, okay? Because that depends on clouds, droplet size distribution, amount of ice, and so many factors. So, although we are good at predicting extreme cold and warm events, we are not so good at droughts and floods, okay? Same thing is true for storms, okay? Extreme storms which occur. Cyclones, for example, okay? We know cyclones will get more intense in the future because of higher sea surface temperature, but whether the number of cyclones will increase, we cannot predict easily, okay? And the other thing is fires. You must have noticed in the last 10 years, there have been extreme forest fires in Australia, Russia, and Canada and United States. Now that's occurring because of global warming and also droughts combined, and that combination is making this creating the extreme fires. But since models cannot predict droughts accurately, we are not able to predict how rapidly the extreme fire events on wildfires will increase, okay? Same thing with severe convective storms. So you must clearly understand that although climate models have made great progress in the last 50 years, they are only good at certain things like extreme heat waves and so on, but not so good at droughts, floods, and extreme rainfall. But I must also tell you, you must differentiate between our ability to predict 20 years from now from what we can do for the next 1 week. The weather forecast models are improved dramatically in the last 50 years, and today the weather forecast over the next 5 years is extremely good. If you are watching your television channel or the forecast given by the India Met Department, you can be quite confident about the occurrence of rain or clear days. Although they may not get exactly the amount of extreme rain, they will warn you there will be heavy rainfall, okay? So short-term forecast is very accurate, but if somebody wants to know what will happen in Bangalore 20 years from now as regards rainfall or droughts, that is very tough, okay? So you must understand the distinction between prediction 20 years from today and the next week. As already pointed out, I will keep reminding you, the major source of uncertainty in a model is clouds. Because a 1% change in clouds has a huge impact on both the global mean temperature and other things like rainfall and drought. So this is where the challenge comes, and the challenge is there because the model resolution is not high enough. A 50 by 50 kilometer grid is not sufficient to resolve many of these clouds, okay? And hence these are put in empirically, and there are difficulties in that, okay? And a lot of research has gone on in the last 40 years on understanding clouds through satellites, through climate models, through field experiments, and we have made progress, but not sufficient to improve our prediction of the future. For example, Dr. James Hansen, a well-known climate scientist from NASA Goddard, he says the new satellites show that Greenland is losing at least 20 cubic millimeters of ice a year. The models don't show that. He is saying this shows that the ice models are almost worthless. It's a strong statement, but he has made it. They treat ice like a single sheet block that is melting slowly. Like you take an ice cube from your refrigerator, put it in the room, it will melt slowly, you can predict that. But what's happening today is not that simple, because the ice sheets and the glaciers are moving, okay? They are dynamic, okay? And they collapse suddenly. So, this is can be seen through this picture of the collapse of some ice in the glaciers. This kind of event models cannot predict. These are catastrophic events which are due to some tipping point in that system, and so our models cannot predict sudden collapse of ice sheets or glaciers, because those are highly nonlinear phenomena. Okay? So, we must be aware of that whatever prediction the climate models are making, the things can be much worse than that, because models cannot predict this kind of event. Okay? So, this is paraphrased by a statement that climate models are built for stability, because the way the models are constructed, we do not expect large catastrophic events to occur. Okay? We do not model for that. So, models cannot be trusted to predict catastrophic events. You should keep that in mind. Okay? So, things like breaking of the ice shelf in Greenland or in Arctic or in Antarctic, those are events which cannot be predicted by any model today. Things are improving. It might change in the next 10 years, but as of now you must realize that limitation. Now, the biggest problem in the model is because of the grid resolution is typically 50 by 50 kilometers, lot of processes are not modeled from first principle. That is, clouds and turbulence are not being modeled based on basic laws of physics. Okay? They are put into the model through some empirical equation. For example, some model may say if the relative humidity crosses certain threshold, say 95%, it will rain. Okay? That is an arbitrary criteria. Okay? It may be based on some field data in some part of Earth, but it is not valid in every part of the globe. Okay? So, this must be kept in mind, that all phenomena related to clouds and rainfall are not to be trusted that much, because they are not modeled from first principles. To show you how this causes uncertainty in the future, here is a simulation from various IPCC models. In the black are models of only with atmosphere, okay, in which sea surface temperature has been known, and then the blue ones are when we have a coupled ocean atmosphere model. The green is when you include aerosol like sulfate aerosol, and the red is when you also include the carbon cycle, how the carbon dioxide is absorbed by the ocean, how vegetation responds to carbon dioxide. So, you can see that in the past 150 years, the model simulation of the global mean temperature is within the observation, which is in yellow here, okay, up to year 2005. But as you go out, you can see there is a large spread in the global mean temperature, because there are variations in the way climate model simulates carbon cycle, aerosol sulfate cycle, ocean circulations, all those, there are differences between models and they cause some variation. So, this is inevitable. So, as you go more and more to the future, there is more and more uncertainty about the temperature. Now, let us come to the parameterization issue in some detail. I have given a sample of the kinds of parameters which are put in empirically in a model, that is not from basic laws of physics. Okay? And there are so many of them here, not a few. Okay? And in this Hadley Center model HADCM3, they did experiments by changing the value they put in, for example, for ice fall speed. The rate at which ice falls in the atmosphere depends on many things. It depends on wind speed, turbulence, and whether there is liquid droplet there or there is a mountain nearby. All those will influence the fall speed. So, we cannot derive the fall speed from any basic law of physics. Okay? So, that number has to be put into the model empirically. Okay. So, when you put it there, each modeling group will do it slightly differently, because based on their own experience in their own country, they will have some data, they will say this is a number it is going to be. And that number is slightly altered, so that finally the model has a good simulation. So, you can see that there are so many parameters here which are put in somewhat arbitrarily. Okay. One of the most important is when air parcel rise and whatever condenses, some amount of dry air is entrained or brought into this parcel. Okay. That determines how far that parcel will rise in the atmosphere. That we do not know at all how much is entrained. It is a very difficult parameter related to turbulence and mixing. Okay. So, every model puts in a arbitrary factor like so much fraction of dry air goes into this parcel. Okay. So, that is not known. So, some of these are completely put in there arbitrarily, and so your simulation depends on those numbers you put in. So, when you develop a model with all these complexities and you first run it, you will not get a good answer. The global mean temperature, which all of us know should be around 15 degrees centigrade, you may not get that result. You may get too high a value or too low a value. Then you start tuning a model. The word tuning comes from the experience in cars. People who have cars, I am talking about cars which use petrol and petrol mainly, and you know that when the car does not work well, you go there and adjust the carburetor so that the engine works smoothly. Okay. That is done by, there are some way to adjust in the carburetor, the way the fuel flows and the way air comes in, and you slightly adjust it. At some point you will hear a nice sound, you know it has been tuned. So, similarly a climate model has to be tuned. We know what the global mean temperature is, and if the model is not getting it, you adjust certain quantities so that the global mean temperature comes correctly, and as you integrate the model for hundreds of years, the model reaches a steady state of 15 degrees centigrade. If there is some mistake in your formulation and the energy balance is not perfect between the absorbed solar radiation and radiation emitted to space, then the system will not reach steady state. So, many modeling groups spend months to tune the model to make sure that they get the correct global mean temperature in the present day, and the model reaches a steady state where temperature will fluctuate, but not more than 0.5 degrees. Okay. So, this is called tuning, and many people think this is very arbitrary. Yeah, it is arbitrary, but you have to do it because there are unknowns in the problem. So, I call your attention to a very nice paper published in the Bulletin of the American Meteorological Society in 2017 by Horden and others, well known climate modelers, and they call it the art and science of climate model tuning. Okay. Look at the title, it is just not science, it is also art, because there is a certain amount of experience and intuition involved in tuning a model. Anybody cannot do it. You need to have spent years with the model to understand how your model behaves and accordingly adjust certain parameters to get the model to get the correct global mean temperature and reach a quasi steady state of 15 degrees centigrade. Okay. So, in this figure they have given an example of how they tune the European Center model called ECAM. Okay. So, let me further discuss based on this paper how tuning is done and why it is inevitable. Okay. For example, they point out that many models systematically underestimate rainfall over monsoon regions, while others will overestimate. Okay. And in the oceanic region, which are very warm, there is a east-west oriented rainfall system called the Intertropical Convergence Zone, ITCZ, which can be seen in satellite data. I will show that later. And you should get that correctly, the location of that, especially in the Pacific Ocean between Peru and Australia. There is a nice cloud band all the way around the equator. You have to get that correctly. Okay? If you don't get it, you have to adjust your model suitably. Okay? So there are many other examples they have given. You can read that. And they have given one example of two models, actually three models here. The Max Planck Institute model, then the GFDL model from Princeton, then IPSL. So in all of them, they tuned them so that the absorbed solar radiation and the emitted long wave radiation both are within around 240 watts a meter squared. Okay? So because that's observed value. All of you remember that when we started the course, we said satellite measured values of this coordinate is very well known for the last 40 years, and they show that it is between 235 to 245. Mean value is 240, which we use all the time in our discussion. You can see that the IPSL model for both absorbed solar and outgoing long wave was too high, okay, depending on the fall velocity of the ice particle. Okay. So finally they did some tuning, and finally they got it in this pink line, okay, this line. Okay. So originally it was well above 240, they got it 240. And you can see that GFDL model, who are very well experienced in this, they got it to within 240 as long as the fall velocity was within 0.5 to 1.5. Okay? And MPI is somewhere here. Okay? So you can see that all these people adjusted the falling speed of ice to somewhere between 0.5 to 1.5 so that the model absorbed solar and the emitted long wave are right. Okay? So that was the purpose of the tuning, and it achieved that. Now remember, this is because these two parameters, the absorbed solar and the outgoing long wave, are known very accurately from satellite data of the last 40 years. But other things are not known so accurately. So you cannot tune for other things because they are not that accurately measured. So they are saying that some models are tuned specifically to get the right answer and some do not. So it complicates when you want to compare two models. It becomes a little difficult. But I would say that a model should do tuning to make sure that they get the present climate correctly. Because if you get the present climate state wrong, then one cannot trust the model to predict the future. For example, suppose your climate model gets the global mean temperature to be 10 degrees centigrade instead of 15, then I will not trust the model to correctly predict the climate change, how much warming will occur. Because how much warming occurs depends on how warm or cold you are now. Okay? So that is a very important issue which many people do not realize, that any time you choose a model for your application, check whether the model correctly simulates the quantity that you are interested in. If it is monsoon rainfall, that model should simulate correctly the rainfall over India in the present time. If the model is too dry or too wet, you cannot trust the model. Okay? So here is one example which I quoted last time. I will repeat it because it's very important. In the GFDL model, they just varied one cloud, how aerosol influence clouds. Okay? We discussed that. It's a very difficult problem. We fully don't understand how aerosol affect the cloud, and they tried three different ways. And the one in red, that simulation called CMRS CM3W got the right result for the global mean temperature change when compared to the observation, which is black. The other two simulations were too cold. Okay. So you can say that the simulation that is shown in red, that is CM3W, is definitely better than the other two as far as the impact of aerosol is concerned. But that is just tuning. We have not really understood why that is correct. So we still have to look at all the three simulations, but you can put a little more faith in the red line, because the red line correctly simulates the variation of temperature over the last 100 years. So in the end of that paper, they say there was a debate among the authors on the idea of using the word art, because some people thought if you use the word art in a scientific paper, people will misunderstand, thinking that this is not a good piece of work. But they said they use the word art as a skill that is attained by study, practice and observation. It is not some black magic. It is something you have gained by working with a model for many, many years. Okay. Now, I just want you to know the galaxy of models that have been used over the last 40 years, various kinds, and I would like to highlight specially how the models improved dramatically in the last 40 years, because there are a lot of model intercomparison projects called MIP. Okay. There was an atmospheric model intercomparison project called AMIP for many, many years. In those models, the sea surface temperature was specified and the model simulation was looked at very carefully. So that is to check the atmospheric model. But if you want to check the coupled model, then there is another set of simulation called CMIP. Okay. CMIP began about 30 years ago, and there by that time, 1995, enough computing power was there to be able to run the coupled model, which has been run for hundreds of years to reach steady state. And in that model, they increased carbon dioxide by 1% per year and tried to look how temperature changed. Okay. That was the basis for IPCC predictions. So it was done by many groups, not one. Okay. And you can see this is various models are mentioned here. Some of them looked at chemistry, some of them look at the past climate, PMIP, which we discussed, and some of them look at decadal variation, some are looked at clouds. So a whole set of models are here in which various groups got together, did the same kind of simulation, but with different models to compare and contrast the models, and thereby learn where the models were not good and where the models were good. So this is how improvements occurred over the last 50 years, because various groups around the world worked diligently and together to come up with good models. So here is a comparison that IPCC quotes for the evaluate climate models. So the black line here is the observation, okay, and the red line is the mean of all the models, okay, and yellow line is individual simulation of various models. Each model is run many, many times, each one of them. Okay, so you can see that any one model can give you some wild numbers, very high, very low. Okay, but if you average all the models, it correctly simulates a long-term increase in temperature of around 1 degree in this period from 1900 to 2000. Okay, but no one simulation can be trusted. But you also note that the multi-model mean was not good for a certain period here around 1940. Okay. Now, I could tell you that could be either due to the data being not that great. Around 1940s we had a world war, so people didn't have time to collect good data. So that could be a reason, or there could be some other phenomena which the model could not simulate. But you can see that after 1960, models have done quite well by and large, except when there was a volcanic eruption. The model slightly over predicted the cooling. Okay. That again could be due to the fact that we don't have sufficient data on the kind of aerosols released by the volcano. Okay. When a volcano erupts, you go and collect some data and it may not be perfect. Now, the same graph is shown again, so that you have a good understanding comparing observation and model simulations and the mean of the model simulations, and showing the three major eruptions which occurred in the 20th century: Agung, El Chichon and Pinatubo. Okay. Both in the case of El Chichon and Pinatubo, the predictions are not so good. Okay. We will continue this discussion in the next lecture.